Professor Jérémie Lefebvre. Jérémie is a mathematician and physicist by training, based at University of Ottawa. Previously was based in Toronto. I actually worked with Jérémie when he was in Toronto. And before that, Geneva, Lausanne, France for a period as well. And Ottawa before that, I believe. So kind of full circle for Jérémie. He's back where he started, physically, if not scientifically. Interesting fact to folks who are not neck deep in the Canadian theoretical neuroscience universe is there's a line of descendants of people of say high repute and high influence and probably high out degree and so on. So Jérémie is continuing that, but before that, his supervisor Andre Longtan, also Ottawa, has been a great influence on many people, both in Canada and beyond, and Mackie before that as well. So pedigree, Canadian theoretical neuroscience pedigree on stage here. And Jérémie's going to tell us about his recent work on white matter plasticity. Take it away, Jérémie.
All right, thank you. Does it sound good? Yeah, okay. John, thank you. Yes, okay, so it's a great pleasure for me to be here. Thank you. I added this slide this morning because I like to start my talks by the end and tell you exactly what we're going to be talking about and what I want to convince you of. And I want to do some form of delay therapy, actually, for those of us who are doing mathematical modeling that use time delays, okay? So I'd like to convince you that white matter is actually dynamic and activity dependent, and that it changes much faster than we think. We like to think that it's a slow time scale. Well, not so much. I want to say that delays are actually structured and are not so random, and just a bit like synaptic weights would be. We think of synaptic weights like a random network. We know that doesn't work. So actually, I want to advocate for the fact that delays actually possess a much more richer structure, and that they play a central role in the dynamics and computations in the brain. And we learn a lot about these by looking through diseases such as epilepsy and multiple sclerosis, which I'll be talking about a bit later. And lastly, and I'm glad Maurizio is in the room because I think the last point is very important, is that we as a community cannot ignore glia for much longer. It's a neuroscience, but I think gradually the field is going towards the understanding that we need to take into account these little guys in the brain to understand what the brain does. And I strongly believe in that as well. So that's the menu for my talk. Very quickly, I just also want to acknowledge the work of a fantastic team of trainees who are pushing most of these ideas forward, just in case I run out of time. So I'll be talking about neuron glia interactions a bit of biology and activity-dependent myelination, which is a new dimension of brain plasticity I'm very fond of. I'll talk about modeling activity-dependent myelination in microcircuits, specifically in the gray matter, and then I'll move to white matter models and talk about pathology afterwards. So is the volume clear for everyone? That's good? Yeah? Okay, excellent. So as a start, I think for me, it's very clear that as all engineered systems we depend on, this is traffic systems or power grids, the operation of these systems depends as much on structure, meaning connectivity, as on the timing of interactions, right? I think it's very clear for a traffic network, you need to have the right things at the right place at the right time for the whole system to actually work. And I think it is true for the brain as well. It's not just a question of connectivity, it's actually a question of timing. And so we've heard tons about white matter, but just as a reminder, white matter is this complicated network of myelinated fibers that sits underneath the gray matter, okay, the cortex, and it's a complicated labyrinth of fiber bundles or axons that are myelinated. Myelin is this fatty, white, lipid-rich substance that wraps around axonal membrane that gives white matter its name and color. And the conductive properties of this white matter are super important, as we've seen numerous times, for the formation of large-scale activity patterns that we see, like eigenmodes, for instance. Yes, there's a cauliflower on the screen. Just making sure that you guys are paying attention, but also because I am not an experimentalist or a clinician. So for me, when I cook cauliflower, I'm always impressed. It looks so much like a brain. With the same structure where you have, the cortex and the gray matter circuits. Underneath this very dense, complicated network of white matter fibers. Anyway, so it's kind of interesting to have a cauliflower on the screen, I think. White matter is very dynamic and changes on the lifespan, and so it's important to understand its properties, as we've seen. So if I was to focus on one axon, it's not just one axon, it's actually an axonal bundle. So it's a bunch of axons that are connected, that are projecting from one part of the brain to another. This is just an illustration. And these fiber bundles are supported by a family of glial cells called oligodendrocytes. So we have our oligodendrocyte precursor cells. They will migrate, proliferate, and start wrapping axonal membranes nearby through a varieties of cues, okay? So they will form these concentric laminae or concentric layers of myelin around axonal membrane, around things we call nodes of Ranvier, which are sites where we have very dense ion channel densities that allow this thing called saltatory conduction, right? So this is a way to accelerate signals very fast. So this is a cross section of a fiber. We have a bunch of axons of different calibers. Each of them is myelinated differently. So it's kind of a complicated story on its own. So speaking of saltatory conduction, for those of you who might not be familiar with it, it's this ability of the action potentials to hop between one node of Ranvier to the next. Of course, that's an approximation. It's not an actual hopping. It's actually diffusion and then depolarization and then diffusion, but that makes it very fast. So we can reach, for instance, in the periphery up to 100 meters per second in terms of speed. If you take that myelin off, then you enter a realm of much slower conduction. So the question is, what's the impact of myelination or saltatory conduction on the dynamics of networks is one of the questions we've been addressing specifically in this conference a lot. What's the importance of delays or the time it takes for action potentials to reach their destination is a big deal, okay? So I take the analogy of traffic again. This is just to showcase Ottawa. We have a beautiful river. This is my home. This is where I do all my, it's not actually my home, so don't try to go exactly there. It's not where I live, but this is where I do my mountain biking right here. And if I want to go to work, then I have to take the many different options. And we all know with traffic networks that it's not because the path is the shortest, it's necessarily the fastest to go to work. I can take a longer path. It's actually going to be faster because the speed of conduction is faster there, or speed of traffic. So this analogy, I think, is very useful to build an intuition for what comes next. So in this very important experiment in 2003, Salami et al. Basically stimulated a bunch of fibers in the thalamus of the mouse or mice here, yes, the ventrobasal nucleus that projects to the cortex along axons of different lengths. And so they stimulated the thalamus and then recorded the cortex at different sites. So if we stimulate over here at this particular site, sorry, I'm just gonna have to do this. I'm sorry. If we stimulate, yeah, I mean old style, blackboard and then this. But if we stimulate here and we have different axons, different lengths, then we would expect if conduction speed is constant that we would first response to the shorted axon, then second response, and third response, right? Because the axons would be different in length. But of course, what they found is that these axons are myelinated, and actually the time delay between the thalamus and the cortex was about constant, meaning that the activation of the cortex takes them basically the same time, meaning that these axons were actually myelinated as a function of their distance. So the longest ones were more myelin than the shortest ones, which is kind of interesting because it means that there's a form of compensation of distance through myelination there. Okay, so that's how these things are actually wired. So in this case here, we would not have space-dependent delays. Okay, this is a part of the white matter that we call the internal capsule, where the time delays are actually not space-dependent. They're all constant, irrespective of the length. Okay, that's just an example. So if we look at textbook examples of myelin on Wikipedia, okay, this is not Wikipedia, but Google, we see usually you have this picture of the axon with these periodic sort of myelin patches, and this is what we all learned. And this is work that Aphrodite has been working on and challenged this idea, this perspective, because myelin that we see in the brain is very patchy. Okay, so it's not periodic at all, like we just saw, like this periodic pattern. It's actually very patchy. And it's not so clear over here, but you have these patches of myelin that are far from periodic. The nodes of Ranvier are not always very small. You have exposed segments of the axons. These patterns of myelination are different in the cortex than in the cerebellum or the white matter. And they are cell-specific, meaning certain cells are more myelinated than others. Inhibitory cells in the cortex are way more myelinated than pyramidal cells. So we have myelination that is patchy, cell and system specific, which speaks of a sort of functional optimization of temporal coordination of neural activation or neural activity or neural projections. Okay, so neural signaling is actually orchestrated by different myelination structures. So now I can talk about the thing I actually want to talk about is adaptive myelination, because myelination is actually not static. We think of this myelination as being something that occurs through development, but actually it's been shown recently that's really very adaptive. So that's an example of video that I need to go and click on over here. So what you see in this video over here, okay, so you have time in hours, okay? And what you're seeing here is actually these myelin sheets forming in real time, or not real time, but accelerated time, okay? So what you see is that actually myelin is adaptive and changes the function of the activity that propagates along the axon. So we know that myelination or white matter is plastic, okay? So in the gray matter, where you would have instances of retraction or elongation of the myelin sheets as a function of activity, you know it's going to also occur in white matter across these longer tracks. We know it occurs during development, especially in early childhood and adolescence. You have these surges of myelination in the brain. Okay, this is developmental, but you also have this activity-dependent mechanism where the more you solicit axons, the more activity that propagates along these axons, the more myelin gets formed. And so for us mathematicians, since we are in the Fields Institute, this means that the conduction delays are state-dependent. It means the more activity there is, the shorter delays become. So if you followed what we've been seeing for the past 4 days or 3 days, networks with state-dependent delays are complicated to understand. It means it poses the question, so what exactly is the dynamic in these systems? This activity-dependent myelination, you could think is sort of an exotic sort of process in the brain. That's actually not the case at all. There's a surge of papers, and this is only 4 of them, but since then there's many more, that shows that adaptive myelination is central for learning. For instance, Paul Franklin, not too far from here, showed that if you impair this ability of myelin to remodel, you impair the formation of memories in a matter of hours. So animals that are prevented from adjusting their myelin won't have the ability to form and store or consolidate those memories. So this is an active demonstration of the role of glia, here oligodendrocytes, in memory that goes far beyond, or I would say arguably beyond, the role of synaptic plasticity, okay? So yeah, I just said that. So neural circuits with activity-dependent myelination, ADM, can be requested as a system with state-dependent delays, fine. And we need to understand these systems in order to make sense of the experiments that are just coming up. Okay, now we have the tools to image and follow white matter pathways, to measure myelin along axons, understand circuit dynamics. So we need to put all these pieces together. So we need to understand how these systems work. So the first part of my research program and what I'll be talking about today, okay, part of it is examining the role of activity-dependent myelination in gray matter circuits, okay? We're doing this various ways. Okay, these are my collaborators or people currently involved in that project. We have access to neural pixels data in animal models. So we use cryptosome to demyelinate the gray matter and look at the recovery of myelination, try to see what happens over there. And so I'll present some of the results that Aphrodite has been working on, which is a postdoc now in Wilton Nicola's lab in Calgary. So I decided to start where I felt comfortable, which is a spiking recurrent neural network. Okay, so I took spiking neurons that I connected to each other. Okay, so I have neurons that are spiking, there are synaptic weights, and axons of a specific length. And each axon has a little oligodendrocyte, if you like, that would modulate its conduction velocity to emulate myelin, basically. So the more myelin there is, the faster the conduction, and then delays would be changing this way. And I will like to make these conduction velocities activity dependent. So the more action potentials that propagate along the axon, the more conduction velocity increases because there's more myelination, the shorter the delay becomes. And I'm gonna let that thing evolve in time and see what happens. Sounds like a plan? Yes, okay, good. So this is the equation for those that are interested. John said you should put more equations, and maybe that's enough. I don't know, but so basically this is the very simple recurrent neural network. We have spikes and we have a state-dependent delay here, and I'm interested in looking at neuron glia feedback. So how am I going to do this? I basically want a learning rule where the more activity I have, the more myelination gets formed, then the faster the conduction, so the higher the conduction velocity is. And so this is the learning rule that I've come up with. I know it's been now explored by other groups, like Steve Coombs now is pushing this idea as well. But the idea is this is just a learning rule that is phenomenological. So it's basically just a way to characterize how the conduction velocity changes a function of the amount of spikes that are passing along the axon. Now, I'm skipping tons of details here. Okay, so of course the dialogue between an axon and the oligodendrocyte is far more complex, but the truth is we don't have tons of data about it. We don't know how they talk. There might be calcium involved, there might be extracellular potassium involved, there might be mechanical cues. There's a lot of different papers and data out there. So here's a form of a phenomenological, that's a hard word for me, by the way, way to describe the process. So when we couple these equations with my network model, I'm interested to see how is myelin going to evolve, basically, or time delays are going to evolve in that system. So I start a simulation where, you can look at the paper for the parameters. There's tons of assumptions here. Okay, by no means is this like applied to all cases, but we start with a case where we create a bunch of axonal lengths in the system. So we position those neurons in space. We have axons of a specific length in between, and then we're just going to give them all the same conduction velocity, like we do very commonly in many models. And I'm guilty of that as well. So this gives rise to very diverse delays, all right? Because the delays are all contingent on the length of the axon between two neurons, okay? And so this is the dynamics I get. I'm sorry, the resolution is not fantastic, but the idea, you have the spike trains over here at the background, you have the mean firing rate over here. What you see is the network is highly asynchronous and with low firing activity. And then you turn this adaptive myelination, so ADM rule kicks in. And then what happens, first of all, things get more colorful, right? I added some orange to make it look nicer. So you have these conduction velocities that were all equal at the beginning, and then they start to increase. As the conduction velocity starts to increase, the conduction delays are becoming smaller, and then the dynamics you get is far more correlated and a bit more intense. So the firing rates are increased in that system, and the presence of correlated variations or fluctuations increases because you allow these time delays to become shorter, but also axon specific. So you're compensating the variability in axonal length by adjusting the conduction velocities between axons. And I'm trying to do this or this networks accomplish this in a autonomous fashion. Yeah, this is what I just said. Okay, so it's possible to achieve these states of higher firing rate and correlated fluctuations in that network using this activity-dependent myelination. Yes. More recently, we've taken the same sort of approach and then start to look at these systems and the impact of noise. Because I want to address this in the room. We are the Fields Institute, and so I think this concept might be familiar to some of you. When you take a dynamical systems with time delays, okay, and you try to find what the fixed point is, time delays have no influence on the fixed point. They will have an influence on the stability of that fixed point, or if you have synchrony, for instance. But the fixed points themselves are not dependent on the presence of the delays. So this annoys me a bit because it sort of says, well, can activity or mean activity in a network or the firing rate increase just because of delays in that system? And if you look just at steady state analysis, it doesn't tell you much information about what the structure of these delays are actually doing. So what we did over here is actually challenge that by looking at the stochastic framework, where we're interested in characterizing not really the stability analysis of the system or the steady state analysis, but look at it from a stochastic perspective by computing the probability density function associated with the activity in such a network. And so this is an example here where we have a network that has very little myelin, if you'd like, and then the activity is asynchronous and of a low firing rate, and then you increase conduction velocity in this to emulate activity-dependent myelination, and the firing rates become more correlated and also a bit more intense. And so the only difference between here and here is the delay distribution, but the fixed point hasn't changed. It's really a manifestation of noise or stochastic fluctuations that interact with the delay distribution in that system. So this is the equation slide. So this is our recurrent neural network. We have spikes, we have synaptic weights, some linear relaxation operator, and we have this stochastic signal that is in this case correlated across all neurons for that particular study. And we did some mean field reduction, so it's possible and relatively straightforward to do that with Poisson neurons, which is one of the embedded assumptions in this work. And you can compute, if you assume that the probability density function for that mean activity is normally distributed, you can compute the mean invariance of that distribution to have an approximation for the probability density function of that variable. So you obtain these ugly dependent and implicit equations for the mean and the variance of the activity in that network. Okay, so they're there. If you want to talk about it a bit later, but the point is that as conduction velocity increases, the delay are becoming smaller. You have a change in the probability density function associated with the mean activity in that network. And the point is that both the mean and the variance of the activity are increasing in that system when you shrink delays or you increase conduction velocity. So to go back to this smile-in aspect, what I'm trying to say is that the probability density function in the stochastic system, which is exposed to fluctuations, will solicit the delays in the system to basically become more intense, increase in the mean, but also more variable. So it's sort of an increase in sensitivity, if you like, or responsiveness to temporally fluctuating inputs that we don't see through steady state analysis, that you need to go through stochastics to actually see that. Of course, if I remove the noise, all this collapses. We asked the question, is the mean delay or delay variance most important in generating these effects? Well, we looked at this same sort of question where we computed the power spectrum associated with the mean activity in that system, which can be computed analytically. And we changed the conduction velocity because you have 3 examples over here, 1, 2.5, and 5 meters per second. But we changed not only the mean delay, but the variance of those delays. How important is it for those delays to be long versus being variable between each other? Okay, and what we found is that, of course, when you have very long delays, so the conduction velocity is small, so you have longer delays. You have these nice peaks we all know, which are reminiscent of synchrony, which is very common in delayed systems. Okay, that disappear as the mean delay is decreasing, or the mean delay is decreasing. Yes, the conduction velocity is increasing. But what you notice is that you increase the variance of the delay, the systems become more and more linear. So it's a bit hard to see, but as you increase the variance of those distributions, of delay distributions, what you notice is that those curves are getting closer to this dashed line, which corresponds to a linear, completely disconnected system. So this presence of delays actually makes the system behave more linearly. And that's the same sort of idea that you see very often in stochastic systems when you inject some noise in a nonlinear system and it behaves more linearly on the action of that noise. So the delay distribution or variability plays a similar role here as making the system behave more linearly. Okay, so I talked about spikes, I think, a bit too long because it's a brain modes conference. I think we have a bias for larger spatial scales, and so part of my brain goes to gray matter, and the other goes to white matter. So of course, for instance, during development, these axons that are connected in different brain areas, so these association fibers, for instance, in the brain are becoming longer, right? And so these longer axons gets more and more solicited, and meanwhile, or the dynamics has to remain constant during development as well, right? So the conduction needs to be adapted. So the amount of myelin needs to change also to compensate for this increase in brain size, for instance, right? And this is a challenge that is faced by white matter, which is much larger. So we examined through the action of activity-dependent myelination, so this ability of the system to change its conduction velocity in an activity-dependent fashion, whether we could preserve the dynamics of this increased correlation, increased firing rate as the brain size would increase. So in this example over here, we took one of the networks we explored in a few slides ago, put them in a little volume, and then increase the size of that cube up to like brain scale, and see whether by this activity-dependent myelination rule that I've described could scale up the dynamics so that the firing rate would be preserved to be very high and the correlation would remain high. And of course, if it's on the screen right now, it's probably the answer is yes. The firing rate would preserve could be preserved, and the correlation could be preserved as well, be maintained very high as spatial scales are increased. And the interesting aspect is that the conduction velocity associated with a different axon were actually scaled as a function of their length. So longer axons were faster and shorter ones were slower, but overall to preserve a delay that is roughly similar among the different axons. Okay. So put that in perspective, we actually got inspiration from work that many people in the room do. So we built a Kuramoto model or a network of oscillators informed by structural connectivity data, where these different axons would be informed by an activity-dependent myelination. So the delays would be adjusting in real time to the activity between those different nodes. An example here where I would have 2 oscillators that are connected with different paths. These oscillators could be Wilson-Cowens, they could be Kuramotos. It doesn't really matter for now. And And my question was, if I want to observe the dynamics across these different networks, whether adjustments in conduction velocity could maintain the synchrony or phase synchrony between different oscillators in the brain. So if I want to have a very connected brain in a particular frequency bands, what are the right delays that myelin should get in order to achieve that? So we used for this particular example the Karamoto oscillator, which we've discussed at length since the beginning of this conference, and we imported some COCOMAC connectivity, so connectivity weights and axonal track length associated with that, and to inform that Karamoto model. And every axon in this model was endowed with a activity-dependent myelination, where we have a conduction velocity that changes as a function of well, two terms, if you'd like. The first one is, I would arguably say, it's a metabolic cost associated with myelination. So if there's absolutely no second term, the activity would just converge toward a steady state value, a baseline conduction velocity, plus a formation term that tries to preserve the synchrony between brain areas. So the more important the phase difference is between two different sites, the conduction velocity would be compensated or adjusted to preserve, if you'd like, synchrony between brain areas. So that example is a bit made up, if you'd like, because I'm forcing the oscillators to be in phase with one another. I just want to pick the right delays, right? And this equation will accomplish that. So that's kind of the equivalent of a cost function, if you like, where I'm penalizing an axon for not preserving the phase consistency between two oscillators. Okay. Nonetheless, so we built that network. So we did the usual quote mark. So we have a brain scale network of Karamoto oscillators connected with one another. We have structural connectivity data. We have axonal track lengths. The usual, ingredients for these brain scale models we all love. And the delays were as usual set to distance divided by some conduction speed, right? And so I get a distribution of delays. And when I look at the dynamics of the system, I get something that is very incoherent. The mean order parameter, if you'd like, of this overall network of oscillator is the order parameter was very small. Okay, I chose a conduction velocity of 3 meters per second in that example. That's something you find in literature quite frequently. And then I turned that activity-dependent myelination process on. Okay, so here it's not terribly visible, but now I have the same. The conduction delays are the distance divided by a conduction velocity, which changes in a function, as like I mentioned in the previous slide, in an activity-dependent fashion. So this is what happened 10 hours later, but it's not hours. It was like a rescaled time. Okay, this should be probably like months or weeks or so it's very simulation time, if you like. But the point is that look at the complexity of the architecture of the conduction velocities in that system. So now the different nodes or different, I would say, axons that are connected to different oscillators with one another have conduction velocities that are very different from one another, okay, in order to preserve synchrony between different sites. And the overall order parameter benefited a lot from these adjustments because we're giving it exactly the delays it wants to preserve synchrony, right, irrespective of distance. Yeah. Another example, which I was very interested in, yes, 5 minutes left. Okay. So another example that I think is very interesting is how is adaptive myelination implicated in the response to injury, okay? Because it's very frequent when we observe patients that have an injury, a stroke, for instance, or other neurological diseases, that white matter is actually reacting a lot to the changes in structure. So what was actually done is that we perturbed this system, okay? So we took the same system we had before, and at a specific time point, I destroyed 80% of all its connection. Okay, so in this case here, where there's no activity-dependent myelination, you have beautiful synchrony. I chose a different regime where you have beautiful synchrony. You destroy 80% of the connection, and then the synchrony disappears because, of course, the system is not as coupled as it was before. But in presence of activity-dependent myelination with the same system, if I destroy 80% of the connection, the remaining ones actually adjust a lot. So the connection delays are actually adjusting, and the connection velocities are adjusting to preserve the overall synchrony of that system. And this is a manifestation, if you like, homeostasis or resilience or recovery to structural insult that can be compensated by adjustment in timing of communication only, and not only structural. So I'm going to skip a lot of details. I just want to briefly mention. 15, not 5. You're the Lord of time. See, It's a perfect example of why delays matter. You know, this is like timing is important. Thank you, John. So I can take a sip of water then. Okay. All right. Okay. I'm going to talk about this nonetheless. I'll just take more time. So just make sure. Okay. So far, what I've told you is all nice. Okay. But it says something. The more myelin you have, the shorter the delays, the best it is, right? This was implicit in everything I've said. The more myelin you add, the shorter the delays, the more firing rates you have, the more correlation you have, the more synchrony you have, all things we like, okay? But more recently, I've been exposed to results that seem to show that when things are when myelin is present in abundance or too much maybe, bad things starts to happen. So this is work from Juliette Knowles and Stanford. So we've been working together, Camillard and with André as well, and Auden, who left us for med school. The results that she found is basically that epilepsy progression is linked to oligodendrogenesis. So basically, she found we can read that together. But the idea is that she exposed these particular rats, okay, the widge rats, and also these particular mice that have a defect in their thalamocortical inhibition. They're a model of absence epilepsy, and you can follow them through the months. And what you see, okay, these lines around these little circles here are actually cross section of the axon. What you see is they're becoming thicker. So this is myelin getting formed. And as you follow these rats, you can realize that the ones that have thicker myelin, or the G ratio is smaller, so they have more myelin, actually are more severely impaired by these seizures. So the seizure burden is actually much more intense in these animals because there's too much myelin. That's a take-home message. So, and she could see also find that the increased myelination occurs in specific pathways of the white matter. Okay, so the white matter itself is its own network, okay? So specific pathways have specific names, but you could find that in the corpus callosum, linking the two sensory cortices on each side, somatosensory cortices on each side of the rat brain, there's an increase in myelination that is pathological. And this fosters a state of elevated synchrony that promotes these seizures from happening, okay? So it seems that we have too much myelin, everything gets too coincident and too synchronous, we also enter a state of pathology. Okay, so this is an example where just to demonstrate the effect is that in these same animals in a mouse line, you can manipulate whether activity-dependent myelination is present or not. So in these animals that suffered from absence epilepsy, if you'd like, you let them run their due course as usual, and myelin forms, and they enter a state of very high burden and seizure. Or you can intervene and block activity-dependent myelination by the use of tamoxifen. And what happens is that you can stop seizure burden or slow it down dramatically because you prevent myelin from forming. So this is an example of a system that is forced to have very small time delays. And actually, it's actually detrimental to the system function because there's, as far as I know, a seizure itself is probably the more correlated, the more synchronous, but information poor brain state we have. Right? So it's not where we don't want that type of synchrony, that's for sure. So the point I'm trying to make here is that that's another example where she follows these animals through time, and what you're actually seeing here is the seizure burden, so the number of seizures per hour these rats were experiencing. And what you see in yellow is what happens when you prevent activity-dependent myelination. There's no other manipulation. You're not destroying myelin, you're just preventing the ability of myelin to adapt or to adjust, which means that it has a profound role in maintaining this homeostasis or this communication or orchestration between different brain networks. So of course, because we're here, we build a model of that. This is work from Camillard and André and myself. So we built a network where, so this arguably would be a brain scale network where we're exploring specific white matter tracks. So I'm interested in two thalamocortical networks, okay, linking the thalamus, so the reticular thalamic nuclei and the ventrobasal nuclei with the somatosensory cortex on one side. It's equivalent on the other side, connected by callosal connection, okay? This is a projection called the internal capsule in the white matter, and this is corpus callosum. And then what we see, we emulate basically what they see experimentally, so they can measure conduction velocity directly, okay, through experimental manipulation. So we can measure the conduction velocity along this track, and we can see that it increases in time. And so what we did exactly that. We take that system, and we manipulate the conduction velocity of signals along this white matter callosal track. and see what happens to the time delays. So that's an example here where you have normal versus pathological or epileptogenic time delays, which are much shorter because the conduction velocity is higher. And what we observe is the emergence of these beautiful seizures, which have the right frequency in the theta range, which is the analogous in the rat and mouse to our alpha, the thalamocortical rhythm in these animals. And you see, as you increase the conduction velocity along these causal tracks, you can see that the number of seizures per hour, their duration, it's not shown here, but their duration is increasing. So that's an example where time delays are actually detrimental, right? So the shorter time delay is actually bad for this system. Okay, it's a pathological shift in time delays and conduction velocity, which I think we should think about collectively as modelers. When we neglect those delays, we might be actually generating or modeling disease states. That's kind of a take-home message I like to deliver. And Camille did quite an amazing work by doing a full bifurcation analysis associated with this system and shown that you can actually shift a threshold for a subcritical Hopf bifurcation by changing the callosal conduction velocity over here. So I'm pretty excited about this work because it shows an interesting trend, which when we think of activity-dependent myelination or gain control of conduction velocity, basically the amount of myelin or the speed of communication along an axon, it seems that if you have too little, you have states of multiple sclerosis or demyelinating injuries, which prevent communication. And if you have too much, then you enter a state of epilepsy or hypersynchrony. So it seems that there's something optimal in between, where you need a bit of communication, so these delays have to exist, but they cannot be too long. Otherwise, we are entering pathologies on both sides. So there's a whole world, I think, when we think about those delays, about their structure and their richness, which we have to think about. And when we think about optimality, we have to think about what are these oligodendrocytes doing? What is their target? What is the cost function they are using to calibrate the right amount of myelin along specific axonal tracks to make sure the delays are correct? This is a question that is fundamental. I don't know the answer, but I'm starting to find the answer. These are closing remarks, okay? So why should you care about this? Well, there's an increasingly large number of diseases, okay? Neurodevelopmental, psychiatric, neurodegenerative that involve oligodendrocytes, increasingly more so, okay? So every year we find a link with autism, schizophrenia, and Alzheimer's disease as well through oxidative stress. Potentially, oligodendrocytes are the prime targets of that stress, okay? They're the first victims of the damage caused by Alzheimer's disease. Okay, so it's something to think about, the implication of these oligodendrocytes in myelination in general and white matter in these diseases. And also, I think what's very interesting is oligodendrocytes and myelin are highly responsive to electromagnetic fields. So I think the fields of brain connectomics or brain scale modeling is getting closer and closer to this idea of neuromodulation. Like we have a network, we have a model, we want to modulate it, and very often we use electromagnetic fields to do that, right? But could it be that our beautiful clouds and networks of neurons could be actually populated by something else than just neurons, and actually oligodendrocytes that are more sensitive to these fields, and we're actually manipulating the myelination directly through these electric fields? So this is the type of hypothesis that we're exploring right now, which is very promising. And lastly, I would say that I skipped tonight, but the timing of neural communication is a central dimension of everything we understand about the brain. One of the most famous rules of synaptic plasticity is spike timing dependent plasticity, which is implicitly using spike timing as its parameter, right? We have pre and post have to be aligned in time to create a change in the synaptic field. But implicit in there is that the timing of that interaction must be correct for the synapse to either potentiate or depress. So there's a direct link between myelination and synaptic plasticity we need to think about. So this is what I tried to convince you today of. White matter is dynamic and activity dependent. Change occur in much faster time scales than maybe you think, or at least I was surprised. Delays are not structured. So this is an example of my PhD student, Grégoire, who was exploring actually structured delayed matrices. So it's not just delay the distance divided by conduction velocity. It's actually an actual spatial structure to those delays and see how it changes the stability and dynamics of the system. And you get pretty amazing results when you look at it in the Huggins spectrum. Yeah. So I think that's it. Thank you for your attention.
Thanks very much, Jeremy. We have time for questions. Maurizio.
Thanks, Jeremy. You didn't convince me that glia is necessary for neurons.
No?
So no, not really.
Okay,
I'm
I
sorry.
wonder why.
Sorry, man. No.
Okay. Because it's the wrong type of glia. You just want to.
Wrong
that's the
one.
science.
Yes,
that's
definitely
it.
the wrong one. No, I have this very quick question I was thinking about. So it's obvious, as you saw in your work back in the days with all the Kuramoto model of the brain, that in the moment in which you break it down and you have this learning rule, you're able to rescue essentially. Yep. And so variability in the glia, right, rescue the rhythm. But just out of curiosity, so could you actually achieve the same, keeping all the connections equals and instead suggesting something at the level of the individual nodes?
So what do you mean?
So you change the Kuramoto properties essentially of the nodes rather than the coupling.
Yeah.
Could you actually achieve the same?
I think with that model, which I hate personally, like I don't want to I want to criticize my own work. I don't think that was a great model. Okay, it was designed to accomplish a task, which is preserve synchrony between different oscillators. So of course it worked, right? Moving forward, I really want to design activity-dependent myelination rules that are physiological and by definition are local, right? Because individual nodes have their own intrinsic dialogue between the oligodendrocytes and maybe nearby axons. And definitely, I think that model, your question is, would it do the same? Yes, I think so. Generally, I think the question is a bit more profound, but my intuition, based on examples I see in the data, is that yes, I think preserving function. So when we look at example of recovery from demyelinating insults that we see in cortisone in animals, you give that drug, myelin gets destroyed, and you look at the recovery, it's surprising how different the myelination pattern is and after recovery, despite the full recovery and function. So there's degeneracy in the myelination patterns that anyway, sort of align with what these models are saying, but next year or something, yeah.
I'm going to grab a question. So the point you're making in the last slide, and I think that's one of your big take-home messages, is that maybe a lot of the things that we think are important in plasticity that we maybe have been focusing on gray matter, maybe there's more going on in the white matter. I think I want to reiterate that point. Like if you talk, you had the slide with electrical stimulation, but basically every kind of non-invasive brain stimulation, maybe with the exception of FUS, because it kind of manages to dodge things in the middle, primarily targets white matter. And this is just well known. Right? TMS fields, they load on white matter more than gray matter. The orientation makes them probably be having an effect on the early part of the axon.
Yep.
The plasticity models in those domains do not focus on white matter, even though we know as a biophysical fact that the primary target of the stimulation fields is white matter. So I think there's a lot to go just at the just to motivate the point. But I think what that leads to is a theory, hypothesis comparison question. So suppose that you have a reliable plasticity effect with some kind of physiological measurement, then the question is that due to a gray matter plasticity response or a white matter plasticity response? And what are the differentiating predictions that you would make under each of those scenarios? And then obviously there's the combination, which would be more complicated.
Yeah.
And I think that's probably a direction to try and think this through as well. Clearly, they'd be quite different, the delay.
I would love to know what the signature of either each is to understand these systems. What is the signature of white matter plasticity versus gray matter plasticity? Right now, it's all measures of synchrony, but these are all blended in these. And as you were articulating the other day about when you're measuring EEG, you're measuring synchrony. So you have both potentially white and gray matter contributions to that synchrony, and also potentially plasticity of gray and white matter combined. So I think we need to
yeah, I mean, if you talk about human neurophysiology, like we just know that stuff changes. We don't know it's white matter plasticity or gray matter plasticity at a basic level.
Well, I'm just gonna say that's why I lied today to you all by presenting gray and then white matter, because what really happened is actually white matter first and then going to gray matter, because this is where I think the details are. Like you have neuropixels data, very high resolution data sets that can disambiguate what is synaptic versus axonal myelination sort of effects. And I think the answers I'm looking for might be more at the gray matter or more accessible to gray matter versus these large scale sort of recordings. Yeah.
Right. Questions, lots of questions. I think we had at the back first.
Hi, Jeremy. Thank you for the nice talk. I have a question. What do you think about epilepsy in MS, where there's a destruction of white matter? Can this framework of ADM offer some form of explanation, or do you need something else completely?
Yeah, I wish I could even say there was an explanation there. I think what I showed is a correlate between increased myelination and absence epilepsy, which is very specifically thalamocortical. But you know, when you have MS and you know, one of the most naive ways of interpreting MS or multiple sclerosis is this spatially diffused demyelination, where every single axon in the brain at roughly at the same time starts to demyelinate at the same rate. Of course, it's wrong. There's a lot of heterogeneities. But I think what you're saying and what I think about is like there's tons of inhibitory projections in the brain that gets demyelinated as well. And so you have a lot of inhibitory control. And that's one of the things that gray matter tells us, is that inhibitory interneurons are actually more myelinated than excitatory ones. So they are predominantly affected by demyelinating insults, including MS. Meaning, so for me, it makes a sense that we have a change, local change in the eye balance that could be epileptogenic due to a loss of inhibition timing, for instance. I don't know if that answers your question, but for me, it makes a lot of sense.
Okay, thank you.
David.
Hi, thank you very much. I was very curious about your spiking network models with the myelin dynamics.
Yeah,
of course.
Yeah, you're gonna talk about phenofactors now, aren't you? Yeah.
No,
okay,
not quite. I was really curious about what you see at sort of after a long time. Do you see that the myelin approaches a steady state, or are there ongoing fluctuations in the myelination level?
So this spiking neural network, the conduction velocity sort of stabilized after a while. And I will not say it's by construction, but because the network is purely excitatory in that case. And so the network was either sitting in a quiet state or a very active state. They had nowhere else really to go. The latest iterations, which are not in this presentation, have E and I cells. And now it's very difficult to calibrate them, because as every learning problem has, you have runaway excitation sometimes. When you have learning plasticity in a purely excitatory network, everything ends up blowing up. So it was a bit the same case here. We just activity that feeds conduction velocity, that feeds activity, excitation, and you have this loop and it just explodes. So you need some form of control. And I was hoping, instead of like manually stop conduction velocity from increasing, I would like to see whether inhibitory interneurons or inhibitory myelination could be that stabilizing factor. So that's the whole like equilibrium is like achieved. I don't know if that answers your question, but
yeah, very cool. Thank you.
Yeah.
Dimitris.
Yeah, great presentation. Thank you. I'd like to go back to this discussion, my favorite, but I hope I don't sound egotistic here, about haptic coupling and cytoelectric coupling. So besides synaptic plasticity, right? Mm-hmm. Because we talked about white matter and gray matter, etc. Plasticity could be an haptic effect in the following sense, right? You have the nodes of Ranvier, which, the gaps that are regulated by myelination. Mm-hmm. And then your work and others show that somehow these glial cells are important for that. Yes. So if something is pathological, right? Things like neuropathic pain, for example, could be some abnormal synchronization between neurons that talk to each other non-synaptically, haptically, or cytoelectrically, through cytoelectric coupling.
Yes.
And this points to a different mechanism, right? This points to not the plasticity mechanism, but still in a crucial role of glial cells and astrocytes, and we have great experts here, like Maurizio. in regulating these top-down effects from the mesoscale electric fields to individual neurons. And I think this is important to put into the
So if haptic coupling between axons,
between
the myelination
Correct.
there plays a huge role in interfering or facilitating that
facilitating abnormal interference. Which should be regulated by glial cells that should act as regulatory, as insulators between neurons. So you have abnormal synchronization. Usually synchronization is a good thing, right? For cognitive neuroscientists. But in this case, because it allows top-down effects that are, shouldn't be there.
Right.
I mean, if haptic coupling effects, then this could be an explanation for diseases.
I would say everything I've showed you today is completely agnostic of the haptic sort of interactions that are clearly present. So I'm guilty of oversimplification, that's sure, but they are, there's tons of effects showing even within a fiber, you have haptic sort of interactions between neighboring axons, and they do like affect each other's excitability in a way that is certainly plastic through glial intervention. And so I think you're perfectly right. I think that could be another dimension of that for sure.
And Jeremy and Dimitri said, if haptic effect is strongest in axons that are unmyelinated, which brings me to a point that I was also interested in. I mean, you have no unmyelinated cells here. Do you think it's worth considering? Really, you have a very bimodal delay distribution. You have a bunch of fast ones and then a bunch of very slow ones. So you just ignore the very slow ones? Do you think they're irrelevant? They're not necessarily adaptively changing. Okay, so the plasticity part, maybe forget that, but just the overall structure of the overall delay structure, there's something like 80 to 20%, sometimes as much as 50% myelinated, unmyelinated axons.
Every axon here was allowed to change its conduction velocity its own way. Aphrodite, my postdoc, developed an axonal model where we have realistic quote mark myelin patterns where we don't have this periodic structure, but we have very patchy myelination. And we look at propagation along these axons where you have like a variety of different excitabilities. And of course, the problem is it was hard to come up with a story with that study because it seems that you have a path dependent sort of effect where depending, every time you enter an axonal segment, where you have myelin, you go at a specific speed, then you're slowed down, and depending on the length of the node of Ranvier or the exposed segment, then you have something else that happens. So you have a dependence on the trajectory of your action potential, depending on the myelination pattern you have behind you. So to put that in the bigger model, I feel I still need to understand these like the link between myelination patterns and overall conduction and delays. That even that relationship is not that simple. So yeah.
Yes. Yes, but I mean, I was just pointing out there are a lot of unmyelinated cells in the white matter. Question here.
Well, thanks for a very exciting talk. It was the first time when I heard about the activity-dependent myelination, and my question is, as far as I understand, there is, loaning for the myelination because it depends on activity, but also the synaptic weights changes as a function of activity. So my question is, do those processes happen in parallel or something is happening at first?
I wish I could answer that question. I feel like a lot of that is unknown. So the relationship between synaptic plasticity and activity-dependent myelination is a very, I would say, new concept or problem we have to deal with. They felt very separate. Clearly, they occur in parallel, but I'm getting to my answer. When you look at signatures of synaptic plasticity in the brain, and you look at signatures of myelination in the brain, it seems like myelination or adaptive myelination, so white matter plasticity, occurs where there's no synaptic plasticity and the other way around, as if they had their own little territory. And it sort of makes sense because when you have an axon and then you put myelin everywhere, there's very little contact site probabilities after that to form new connections or axonal synaptic sort of new synapses. So you can think of myelin this way as a way to stop or consolidate memories and fix them so that they become less plastic. And it goes with this idea of consolidation of memories. So yeah, when these memories are formed, then they get myelinated, and then they become less plastic as a result. So they got solidified, if you like. And so in that regard, you could think of synaptic and axonal plasticity as being distinguishable, I guess, from each other, or being two separate processes. I don't know if that answers your question, but yeah, happy to talk about it more.
Okay, thank you.
All right.
Any other questions?
Okay, good.
Yes.
Hi. I just wanted to ask, like, if you consider that this adaptative myelinization might be useful to synchronize the time of arrival of sensory inputs. So, like, we get many sensing that sense that are sensing the world in parallel, and so there is a lot of redundancy in there, and the brain will know that maybe if one bundle of fiber is become faster than the other one, that it has to myelinate to compensate, so the information are in sync, and to synchronize the.
Yeah, I think.
I don't know if my question is
yeah,
clear.
So this is called like a retrograde sort of learning, if you like, where an error message is sent back to the oligodendrocytes or the population of glial cells to compensate, say, hey, produce more myelin to keep up. But there's no such sign right now, at least from data I was exposed to with these labs and in this very little community about what could be the signal that tells the oligodendrocytes there's not enough myelin. So we know that oligodendrocytes myelinate multiple axons, or maybe they're all myelinating those axons at the same time, and these different axons are those that are being compared in terms of speed. But yeah, but there's no such sign of a mismatch, I think. Yeah.
But my point was that maybe it's not the signal that is like that there's no signal, but so the coherence comes from the fact that the world itself is coherent, and that sensory input across different modalities and all will tend to be synchronized. Like you will hear a big sound when you will see a big flash, and you will, and like that, the myelin fiber try to get the information inside based on this beliefs on this generative model. I'm mixing everything is the end of the conference, but I'm not sure you get my point.
I think I know where you're getting at, but maybe I'm not answering correctly. Maybe I just don't know what the answer is. Or so I guess we could chat about it. But that question is a very profound one. It's like what it like how do we know? So the synchrony itself could be. So I think you're saying that synchrony could be used itself as a signal. Yeah, so you need a detector of synchronous arrival in this case, right? Anyway, we could maybe talk about it. I don't know what we're doing on time.
No, we're good for time.
Okay.
Last question from Matthias and Jacob. Could you come up, get set?
Yeah, that might be a very naive questions, but now you talked a lot about processing increasing the conduction velocity. But I mean, aren't there also, or shouldn't you also think about processes decreasing the conduction velocity, because otherwise the whole system is just blowing up? So what's happening there?
There is myelin retraction. There's such a thing. So in systems where activity is like where it has been observed, where you have a decrease in activity along specific axons, you see a retraction of myelin sheets. That involves a combination of factors. You could have perinodal astrocytes. There's a bunch of different factors involved there, but it's part of the experimental sort of portfolio of retraction and elongation. Otherwise, indeed, you would just have increase and then that's it, right? Yeah. So there are axons that seems to go deliberately slower, and Very interestingly, I was talking about this morning, where you have actually axons that have a suspiciously tortuous path away from their target, as if it was a deliberate detour. And the question is why, since we know the brain is on high metabolic demands, like everything must be efficient, what takes so much of a long path? Then one of the hypotheses is that, well, perhaps as a control of latency through like, let's take a little detour, get a coffee, and then get to our target. But yeah, so decrease in conduction delay is also something that seems to be there, at least in the data that we see. For the retraction data, I don't know. I couldn't answer, but I could maybe look it up and we can talk about it. Yeah, I don't have this information in my mind. Yeah, okay, great.
Great discussion, guys. And we should, should, and will keep it going after the session. Final round of applause for Jérémie for an excellent talk. Real tour de force.